All right, this video is going to go over the boiling curve. I just learned about it about a month or two ago, and I thought it used some pretty neat heat transfer, so I want to go over it here. So, what is a boiling curve? Well, it's this plot that I haven't filled out yet. The x-axis is delta T. So in my example, I'm going to be using water flowing through a pipe. So the delta T is going to be T pipe minus T water. So we've got our T pipe down here. And then T water is just T water. Cool. This Q is heat flux. So how well can heat transfer from the pipe to the water? Now you're probably thinking, as delta T goes up, heat flux should increase, because in heat transfer you learn that for conduction and convection, heat flux is H delta T. I don't even need the parentheses there. H delta T for convection, or what is it? K over L delta T for conduction. So in both cases, as delta T increases, the Q should increase. Well, that's not actually the case. So the actual boiling curve, it goes up until point C, or between point C and D. Then it goes down, and then it goes up to infinity. Cool. Why does it go down and go back up? That is the main question for this video, but I'm going to go through points A, B, and C before I even get there. So, all right, point A, what's going on in point A? So here you've got a very low delta temperature between the wall and the fluid. Let's also say that the, what's it called? T water, that's not enough space. That is terrible. Is less than T sat. So the water temperature is below the saturation temperature. So what happens? Well, you've got super hot wall on the top and the bottom. They will cause small bubbles to form. Let's say they cause a big bubble to form. The bubble, since it's full of steam, it's less dense than the water. It'll go up through the water. This will do a couple things. One, it'll mix the water as it flows up. So it'll cause the water to mix. So this bubbling causes natural mixing, which is pretty neat. The more important thing is as the bubble goes up, it'll get smaller until it disappears. Why does it do that? Well, because the water temperature is less than saturation temperature and steam is at saturation temperature. This is T sat T water. Heat's gonna transfer from the bubble to the water. So as the bubble goes up, it'll transfer more and more heat to the water, and eventually it'll just be all gone. So that is the first region. Second region, region B. So here we've got T water equals T sat. So now we're starting to make steam. And for reference, Yeah, I guess from this point on, what is it? T. Temperature, heat. Yeah, from this point on, we're going to be in the mixture region. So the water temperature is always going to be at Tsat. Cool. All right, so here, now we've got bubbles. But as they go up, they still cause the mixing. But the bubbles don't get smaller. And that is because these temperatures are equal. So heat doesn't transfer from the bubble to the water or from the water to the bubble. So the bubble just stays the same size. Cool. Region C. Now we've got bigger bubbles. So I don't know why people split region B and C into two different groups. They're kind of the same group. Yeah, region C is just, you've got a lot more bubbles now. So you've got a lot of bubbles and they group into bigger bubbles. That's all that region C is. Region D. Now we start to get interesting. So region D, I think it starts at 212 Fahrenheit. Maybe not exactly there, but the idea is if this surface, that's a terrible one, if this surface is at the boiling point of the water, we can't have water touching it. We can't have water touching it. So what's going to end up happening is there's going to end up being a vapor layer that forms where the thing touching the wall is steam. Because if water touches the wall, it'll just turn to steam because the wall is hotter than the saturation temperature. So yeah, you get two vapor layers and the middle is full of water. Now, why does this curve go down? Well, it goes down because vapor layers suck for heat transfer. And that's because before, you've just got conduction from the wall straight to the water. Now you have conduction through the wall, through a vapor layer, and then to the water. So that adds a vapor layer. And by default, that adds thermal resistance. Oh, I erased too much. And if you add thermal resistance, with our total stuff, or should I write it here? We're adding this convective term, which by default adds thermal resistance. And we know that Q equals delta T over R total. So even though delta T is increasing, it's a bad arrow. Even though delta T is increasing, the R total is increasing more, and that causes this downtrend. And the kind of the key reason for that is as the delta T increases, the vapor layer becomes thicker. that's because there's a thermal gradient. If you're at like, oh, what happened there? All right, anyways, if you're at like, so boiling's at 212. So let's say you're at 300 Fahrenheit at the wall. Because, right, it starts at 212. Well, it might start at 212. I'm not too sure. The temperature of the wall increases as you go further to the right. So let's say around here, you're at 300 Fahrenheit at the wall. There has to be a thermal gradient. So it'll go up to, let's say, 212. Because the vapor layer will happen at where the gradient is 212 Fahrenheit. And let's say you're farther down and you're at 400 Fahrenheit, the vapor layer will be thicker, but it'll still be 212 at the vapor layer, or at the vapor surface. So yeah, the main reason for this downtrend is now you're having to convect heat as well as conduct it. So it's more thermal resistance, and the vapor layer gets thicker as the delta T gets higher. And that sucks for heat transfer. So this point, what's it called? Leidenfrost point. I don't know. But that's just what it's called, so I'm writing it there. All right. Now, for point E. Well, what should I draw? I'm going to draw this arrow, and in yellow, I'm going to say Q convection equals H times delta T. No. Is it T-wall? T-pipe. Cool. So that's our convection equation. But anyways, let's move on. So point E, it'll look very similar. It will look very similar, and chances are the vapor layer will be narrowing in. So the vapor layer will be thicker. But now, in addition to the convection, we also have radiation, because the wall temperature is so much hotter than the water temperature that radiation will come into effect. So what's the equation for radiation? Cool. Why does this start to go up at a certain delta temperature? It's because these terms are squared, or to the fourth, actually. So up until the Leidenfrost point, this term overpowers, which is why the heat transfer goes down. But after the Leidenfrost point, the radiation overpowers, and it'll continue to overpower because its temperatures are to the power of the fourth. So the heat transfer becomes really good after that. But yeah, that is about it for the boiling curve. Pretty neat.